The answer is none of the above. All you have to do is look at the 2 points around 19. First of all, the first one is never going to be true. Why? The data is from 65 to 95. So the moment you say 2005, you're already talking about extrapolation. Okay? So very difficult to use regression or prediction for data outside of the range we have collected. The other two, the 100 seconds and the 50 seconds, look at the tail points. Okay? If you look at between around 85 to 95, there's hardly any decrease. Similarly, if you look at between 1965, maybe 68 to 72, 73, there's very little decrease. So the two statements, 100 seconds and 50 seconds, applicable maybe for the line or the part of the data with the greatest slope. Okay, but for the other points, it's not necessarily true. And if you can find one exception to the rule, you can't answer it as yes. Okay, that's really the end game.
It's wrong, isn't it?
It's actually right. It would be positive, but we cannot determine the exact value. Why? What is correlation? Correlation is a measure of linear strength between x and y. Okay. In this particular case, we have a relationship between x and y. Soil is equal to 0.4 plus 1.3 times flow rate. What is that 1.3? Slope. Right? If the flow rate increases, wouldn't the soil erode more? Because, in fact, by a rate of 1.3. Guy, please. Thank you. So, when we have a positive flow rate or positive slope, what is it telling you about x and y? The relationship is positive. So, we know that correlation exists. But we have nothing to calculate with. Therefore, we know because the slope is positive, correlation is positive. But the exact number we can't calculate based on the information. Okay. So in this particular chapter, we are now going to start looking at how to collect data. So let me refresh your memory on what we have done so far. In chapter 1, we saw how to present the data that we have collected in various forms. In chapter 2, we looked at how data is in terms of distribution, in terms of relationship between x and y, in terms of scatter plots, regression, so on. But where does this data come from? Well, data invariably comes from multiple sources. And we are going to look at two main sources, observational studies and experiments. And then within that, look at different ways of collecting data. But one thing which we did do and which we should have done in probably chapter 1 or chapter 2 is know that we are using certain distributions very frequently. And one of the distributions we use very frequently is the normal distribution. Why do we use the normal distribution? Because many things in life tend to follow the normal distribution for us. Okay, a lot of the regression analysis follows normal distribution. Well, for us, fortunately, if I give you a data set and ask you, does this follow a normal distribution? There is an easy way to test it. And the easy way to test it is something called the normal quantile plot. And we will generally use JUMP to plot this. So when we actually do regression analysis, I will show you how to plot the normal quantile plot. But for the moment, I'm just going to give you the background behind it. Okay? So in a normal quantile plot, what we do is we rank the data points and then compare the ranked data with what we would get from a normal distribution. If what I rank and what I get from the normal distribution happen to be similar, then if I'm plotting one against the other, you will get a straight line. Okay? So as long as you get a straight line between the data that you have ranked and a value coming from a normal distribution, we say that the data happens to follow a normal distribution. If the data does not happen to be a straight line, we say that the assumptions of normality are violated. Okay, so how does this look? So I'm going to show you how it looks. So the data on the left If you look on the y-axis, that's your ranked data. The data on the x-axis is data coming from a normal distribution. Plotting one against the other appears to give a straight line. So the data on the left, we would say, appears to come from a normal distribution. The data on the right side does not appear to come from a normal distribution because why? The data when we plot one against the normal distribution values is not straight. In fact, if you look at it, in JUMP, what it will do is very simple. In JUMP, it will give you something called a confidence bar, something like this. And the line will be in. As long as the line is inside those two bars, we say that it is straight enough. In this particular case, the bars would have been something like this. And therefore, the line is outside of those bars. Therefore, it violates the assumptions of normality. Okay. So JUMP will give you a graph which will have two bars, and within that the data points. As long as the data points all lie within those two bars, we say the assumptions of normality are satisfied. So that's called a normal quantile plot. Okay. So that's something that I left out when we did chapter 1 and 2. And the reason I bring it is for obvious reasons. You have a question on that in your exam. So, okay, so let's look at chapter 3. How do we get data? Well, the easiest way to get data is what we are already doing for milestone 1. Use available data. Okay. Now, it's fine when you want to do analysis based on available data. But even the available data has to come from somewhere. Okay. And for us, we have to figure out, where does this data come from? How reliable is data? What can I use it for? And what conclusions can I make from this data? Okay, that's really what I'm getting at. So, how about anecdotal evidence? Have you heard anything today from anybody? Want to give me anything which is anecdotal evidence? So you guys, I see many of you studying for your business management quiz in the next period. So what is your opinion about the class? Yeah. Hate it. Okay. So let's just stop at hate. Let's concentrate on the 4 letters. Okay, hate. In this case, hated, right? What kind of evidence is that? Strong. Okay, let me give you a hint, okay? Yeah. That's right. Anecdotal? No, anecdotal. Anecdotal evidence. No, sorry. Okay, that's and the problem with that is what? It's always biased. That doesn't mean that your evidence may not be true. But if I were to just take your evidence and based on that evidence conclude that business management class is bad, right? Then that would be coming to a conclusion with most likely biased data. How would I go about getting a slightly better picture of that class? What would I have to do? Me? I don't want to. I have trouble attending this one. How would I get a better picture of, when I say better, yeah?
Test scores.
Whose test scores? His test scores?
Their test scores. Like students who are happier with the class will probably have higher grades than the ones who aren't.
No. That's nothing to do with. The test scores really reflect whether you like the class or not. I'm sure many of you here might be getting really good test scores, but probably hate this class. How many of you hate this class? That's it? I'm not doing a good job. I should ask a more relevant question. How many of you hate me? I'll leave that out for the moment. Okay. But that is, scores have nothing to do with whether a class is good or bad, right? How would you get a better opinion? Let me put it that way. Ask more people. How would I ask more people? I mean, I asked him. Somebody else here said hated. Yeah. Anxiety of the quiz. So I have 2 people now. Both of them say hated. 100% conclusion. It's a bad class. Oh, there's one more person nodding. At this rate, the whole class will be nodding. Yes, yes, yes. So how do I fix this problem? It may be true that every student hates that class, or it may be true that that class is really bad, but I need to get a more informed judgment about it. How would I do it? Yes?
You could stand at the door when everybody walks out and be like, you hate this class.
I could do that.
Just an idea.
So what would that be called if I were to ask every student? Okay. What do you, it's a survey, but in specifically if I ask every person who's involved in the class would be called, we do that every 10 years, a census. Right? When we count every person involved in that particular, whatever it is, it really is a census. Right? And if there's one thing I know about myself, I'm lazy. I never want to take a census. It's too time consuming, okay? So what you want to do is, but you're right. The better opinion is to ask everybody who's in the class to see what they think about the class. And I would then definitely get the opinion of the class. Okay, good. We are already going. So I don't even really need to teach this chapter, but I'll just do it. Okay. What we really need to do, therefore, is to come up with a way of figuring out the information that we need in a constructive or scientific fashion. And that is what we call as designing an experiment, okay? Or in this case, even an observational study. And I'm going to talk about the difference between an observational study and an experiment very soon. So let's have some definitions first. So let's talk about the difference between population and samples. Okay. Population is a group that contains a set of individuals or items of interest. So if I'm interested in figuring out the average age of a person at Kent State, the population would be the set of all students at Kent State. If I'm interested in figuring out whether people like the business management class, then the population would be the set of all students taking business management. Notice the population changes based on your objective. Don't just say the population is Kent State. Makes no sense. You have to have an objective to define the population. So if I'm interested in the average income of a person in the United States, then the population would be the set of all people in the United States. Again, a population is always with reference to an objective. A sample is nothing but a subset of the population. So the whole objective is, can we tell something about the population based on a sample? Okay, can we tell something about the population based on a sample? Why? It's very difficult sometimes to get the whole population. Okay, let's say I'm doing quality testing, okay, and I'm testing hand grenades. How would I know whether a hand grenade is quality or not? How would you figure out? I mean, if let's say you are in charge of quality testing of hand grenades, probably your dream job. Probably not. A few people who might throw a hand grenade at me right now, but okay. How would you test it? How would you know whether a hand grenade is working properly or not?
Pull the pin and throw it.
Okay, you pull the pin and throw it, and when it explodes, great job, right? So if I want to test, if I give you a shipment of hand grenades, and that's my population, and I say, oh, can you test for quality? And if they happen to be all of good quality, how many hand grenades do I have left? I have none. So I can go back and say, oh, great job, you guys manufactured excellent hand grenades, but I have none left. So obviously we can't even test the whole population. So what we want to do is to take a sample from that population. Maybe I'll take 10 out of the 100. And I'll test those 10. And based on the results of those 10, make some conclusions about the whole population. Okay? That's a sample. The 10 would be the sample, the 100 would be the population in this case. A value that we calculate from the population is called parameter. So the population average. So if Kent State is the population, the average age of a student at Kent State would be the population mean, and that would be called as a parameter. This class would be a sample. The average age calculated of a student from this class would be a sample statistic, which would be the sample mean. So what we are trying to do is, can we use a sample mean to predict the population mean? Based on the average in this class, can I predict what's happening at Kent State as a whole? That's called statistical inference. Statistical inference is to use sample data to make inferences about a population. In this case, the value calculated from a sample is called statistic in general, and the value calculated from a population is called parameter. Very easy to remember. Population starts with a P, parameter starts with a P. Statistics starts with an S, sample starts with an S. Okay? So the question is, why sample? I've already given you example on why, on one example, why we have to sample. But sampling actually is obviously less time consuming. But here is the surprising thing about sampling. Sampling can actually give you better results, more accurate results than a population. Can you think of why? Do you know what kind of problems we have with the census every time we do it? People lie, that's true, but what else? What other problems do we have with the census? Sorry? They don't fill a non-response. What else?
If you don't have an address, you can't fill out.
There are a lot of people who are never counted. Okay. So there are a lot of underrepresented groups, missing groups, invalid information. And think about this. What is the population of the United States? It's crossed 300 million. Can you imagine the task of counting every single person? 300 million of them. Lot of problems. Okay. So you can actually design a well-designed sample that will give you more accurate estimates of the true population characteristics than using a census. The only reason it's not implemented is politics, not from a statistical point. Okay, but sampling therefore can actually provide you with a more accurate representation, because when we're dealing with large populations, all kinds of problems arise. So sampling is, I'm going to show you a simple experiment, and you're going to actually do it and see if it's true. So I'm going to give you 15 seconds to do this. You see the statement in red? Can you count the number of F's, F's as in foxtrot, in that statement, in those 3 lines? So let's see. So 16, 31, 40, 44. Nearly 40% of the class got it wrong. You might tell me that if you actually had about 2 hours to do this, you'll get it right. Well, this is just 3 sentences. Now try counting 300 million people. Okay, so if you are so let's start with observational studies. There are 2 main distinctions between how we collect data. The first set is set of what we call as observational studies. Studies where we don't actively tell or do something for the data to be generated. So, for example, if I want to find out how many students are talking in class, I could just stand here and look at the class and note down the value. I'm collecting data by observation. Okay. The other approach is by experiment. Okay, that means in an experimental study, I, as the experimenter, will tell or ask these people to do something specifically. So I might, if I'm interested in figuring out whether my teaching methods are useful or not, at random I might assign some of you to one class and the other people to another class. You don't get the choice. I get the choice to tell you which class you're going to attend. And then observe what happens in each of the class. When I actively allocate or assign, in this case you, to a particular class, that becomes an experiment. It's no longer an observation. It would be an observation if you chose the class and then I observe what was happening. If I were to make the assignment, it becomes an experiment. Intuitively, and compare observational studies to an experiment. Which of the two strategies is likely to lead to results that we can rely more on? Intuitively. Experimental studies. You know why? In an experiment, I can control for a lot of things. Suppose I give you the choice, okay? Wouldn't you choose a class based on certain tendencies? Right? Either I like the instructor, I don't like the instructor. I like the teaching style, I don't like the teaching style. I like the class, I don't. So based on certain tendencies, you will choose a class. But when I assign you, I'm going to do that at random. So in one class, I might get people who like the class, I might get people who don't like the class. I might get people who like the teaching method, I might get people who don't like the teaching method. So the results coming from that class will be more representative of the population. So in an experiment, we can control for factors or situations that are normally we can't have control of. When we can control for these extraneous things, the results are much stronger. One way or the other, it doesn't matter. So most times when we are doing studies and we are trying to understand causation, that means X causes Y, really the only way you can get to X causes Y is through experiments, not through observational studies. In the case of the lung cancer and tobacco, it was such a long study that we finally could say it's causation. But in most cases, X causing Y is usually based on some kind of an experiment. Okay? Oh. So in an experimental study, we deliberately expose it or impose a treatment on individuals. So I'm going to use some terminology. Whenever we use people as part of the experiment, we call the people subjects. Okay. A treatment is something we impose. So that means, let's say I have two teaching methods. Each teaching method is a treatment. Okay, so one set of people will get treatment A and the other set will get treatment B. Okay, so that's a treatment. Unfortunately or fortunately, observational studies are a large part of how we get data. In fact, all the data that you have been using for your milestone and for your project is based on observational study. Right? Because you have just gone and collected it from somewhere else. But if you're going to do a cause and effect, usually the only way we can do that is through an experiment. We already talked about confounding in the last chapter. Now, confounding unfortunately happens a lot more in observational studies than experiments for the same reason. In an experiment, we can control for a lot of things. Once we can control, we can also understand confounding much better. But in an observational study, we have no control. You are what you are, and I have to collect the data as it is. Okay, so in that sense, we have no. So here is some terminology. When we use people in an experiment, we call them subjects, or in general, they are called experimental units. Something that we apply to our subjects or experimental units is called a treatment or a factor. So let's say a factor could be teaching methods. And that factor has two levels, teaching method A and teaching method B. Teaching method A and teaching method B are two treatments that we apply to the subject. Okay? So we can have multiple factors. One could be teaching method, one could be classroom type. Classroom type could be three types. One could be a large classroom, one could be a small classroom, and one could be sitting under the tree. And the way we are going, we might land up there. Okay? So in this case, we have how many treatments? For the first factor, we had two treatments, teaching style A, teaching style B. For the second factor, classroom type, we had three treatments, large classroom, small classroom, outside. How many total combinations, therefore, do I have? If I can have two of one, three of the other, how many total combinations? Not. A person can be assigned to one of 6 combinations, right? It can either be classroom, large classroom, teaching style A or teaching style B. Similarly, small classroom, teaching style A, teaching style B, outside, teaching style A, teaching style B. So the total number of treatments in that experiment would be 6. Okay, that's how we do experimental studies. So we already talked about this. This is a key word, so please make sure you understand the meaning of this. Something is statistically significant if the results from that experiment or study is far greater than that you would expect by chance. Okay. We will have specific tests to see if a result is statistically significant. But the moment I use the word statistically significant, that means you can be rest assured that the conclusion is that the effect is far greater than you would get by chance. Okay, that's the first thing. So here is the thing. Let's see if we can identify that. We had 150 patients were given a drug and 150 were given a placebo. The researchers counted the episodes of pain in each subject. Who are the subjects? The patients, right? How many of them we have total? 300. What are the factors and treatments? The drug, basically, and we have two treatments. We have a drug and we have a placebo. Okay. And what is the response? What are we studying? We are studying specifically episodes of pain, right? So that would be a response. Okay. Anybody here been involved in a drug clinical trial? Oh, I shouldn't probably ask that. Anybody? What other trials do we have? Anybody involved in a trial? If you're ever involved in any kind of an experiment, okay, they always, if you read the disclosure form, they'll always tell you that you may or may not be given a drug. You may be part of a control group. But you will not know that till the whole experiment has concluded. Why? Because when you have to do a performance of the drug, you're comparing it against some group, and that group is usually called the control group. Okay. Now here is the, do you know why we have, oh, this is actually interesting. I'm sure it's probably after this class you'll be taking headache medication. So what is your favorite headache medication? Nothing? Advil? No. What? No. Tylenol? How many take Tylenol? Okay. Oh, how many think Tylenol is the most effective medication for headaches? That's okay. What else? Advil? How many say Advil? Okay. What did you say? Aleve? How about Aleve? Okay. The rest of you don't get headaches. No headaches. So why is it that we have so many different medications for headache? And if you look at the advertising, and if those of you in marketing probably know this, everything is number one. Right? Aleve is number one for headaches. And if you look at another billboard, it'll say Tylenol is number one for headaches. What is it? How can they all claim to be number one? They don't know how to count behind one? What is the deal? Why is all the medications number one? Yes?
They're all number one based on certain data.
So, and basically they made up their data, or
They just pulled it from different, I guess.
different groups?
Yeah, different.
Okay. So that's fine. But how is that they're able to claim that they are effective? Yeah.
Well, some people will have different reactions to the different kinds of.
Okay. So one of them is that the chemical compound is slightly different in each of the drugs. So it creates a slightly different effect. Okay. But they're also claiming that, right? But do you know how FDA approves drugs? When FDA approves drugs, all they have to show for a drug manufacturer is to show that their drug is more effective than somebody who's not taking the drug. They do not have to show that their drug is more effective than all the other drugs that already exist. Think about this carefully. That means a newer drug may not be the most effective drug on the market. You see this? So if especially for people who are suffering from high cholesterol and all, some of the older drugs or high BP, some of the older drugs are actually the most effective drug. In fact, the most effective drug for blood pressure medication is a diuretic, which has been around for about 30 years. Okay. Because of the way FDA approves it, so if I create a drug which cures headaches in 51% of the people compared to the 50% in the control group, I can claim my drug is effective. I don't have to show that it is necessarily more effective than Advil, Aleve, Tylenol, etc. Okay. So remember this. Next time you're trying to buy a new drug, just ask yourself the question, is it the most effective drug? Most likely the answer would be no, unless it's a drug for a new treatment. Okay? So, but in any case, we do comparative experiments, and we compare them to many other things. One of them is a control group, a group of subjects that does not receive any drug or pill. Okay? This is usually, so we know we have a baseline to compare against. Many of you know about placebos. We can do placebos in many ways. We can either have it which looks like a pill, but sometimes mentally do you convince yourself you're fine even though you might feel sick and you actually feel fine? That's part of the placebo effect. That is, if you're given a sugar pill and you don't know it's a sugar pill, you might think you're getting an effective drug, and it works sometimes. In fact, the placebo effect is really large, around 30%. Okay, so there is a lot to be said for the placebo, but so whenever we're doing an experiment, many times all you are getting is a placebo. Okay, it's a sugar pill. So, but placebos can also have a negative or a positive effect. In one sense, this is, in sports especially, they talk about this level of confidence, right? If you're winning, you're really confident and you continue to win. In some sense, that's like the placebo effect. Why? Because you're convinced, okay, look, even if things are not going well, you can come out of it. Okay. So when you're taking a drug and you don't know whether it's a drug or not, you think it's a drug and it's having this effect inside of you. Okay. So. And the last one is actually interesting because a placebo can have a negative effect. And if you want to understand that, the perfect example is today's economy. Even if you are, well, actually, the median salary for the country has dropped by, I was going to say about $5,000 to $10,000 in the last 3 years. The median. Think about this. So your earning power has actually reduced now, even if you got a raise. compared to 2-3 years back. So what happens is it's got a negative placebo effect in some sense. That is, if you think that the economy is going to get worse, guess what? Probably will get worse, even if it were to actually improve in terms of numbers. Okay, that's the negative effect, and that is true even for drugs. So we've seen all that. So let's talk a little bit about biases. The idea in collecting data is to predict this point. This is where we want to be. We could collect data that looks like this. What is good about that? The good thing about the data that we have collected is it's got low variability. What is the bad? It completely missed our bullseye. So, the low variability actually created a problem. Why? The smaller the variability, more likely we are going to miss the bullseye. Compare that to, for example, the one right below this, okay? This has high variability and a bias. Both, it's the worst kind of situation. Both high variability and high bias. What we are looking for is data collection that looks like this, but invariably we will never get that. What we are likely to do is get something like this. That's what we want in the end. Okay? So ideally we want something which has low bias. That means on average, the data tells us something about the average of the population, and the data has low variability. That is our objective in data collection. Okay? So, and the way we want to avoid bias is something called randomized. Note, that is the key word for us. Notice that I'm not really going through the techniques. We are really not going to apply all the techniques for data collection, because for most of the analysis we are going to do in this class, we are going to presume we have the data. Okay? What I'm just showing you is some of the techniques that are used to collect this data. One technique that we will use, in fact, should be used all the time for data collection, is the idea of randomization. Randomization allows us to remove the inherent bias that an experimenter may have in collecting data. So, if I want to pick a random sample, if I want to pick a sample from this class, I should randomly pick the students. And how can I randomly, suppose I want to pick 10 students at random, how would I do it? Oh, you just, okay. How would I do it? Pick 10 students at random. Names in the hat, and then pick 10 names at random. That would work. Okay, yes?
Hand count.
What?
Hand count. A hand count.
Hand count of what?
You pick a student and you select the number to how many groups to a certain number, and the students count off the number, and that's the group they're assigned to.
Okay, you confuse me now.
You just randomly point to people that are in the class.
Well, would that be random is my question.
I mean, if you close your eyes, it would be.
No, really?
Sure. You can't see who you're picking.
So I'm randomly pointing. Who am I pointing to?
Well, you're pointing at the side.
It could be. I don't know. I mean, I guess I could randomly point or throw things. So that's possible. But I'll rather go with a hat.
Yeah, but in that instance, not everyone's going to be in class.
Well, then if I randomly point, if they're not in class, who am I pointing to?
But you can't point at somebody who's not here.
No, the names in the hat would be the people who are in class, right?
Not exactly. Not if you took the whole class roster, whatever.
Oh, no, I won't go that far. I'll make you write your name and put it in the hat. Okay, so. Or we could do what is called as a double-blind experiment. So last class we were talking about producing data. In this class, this particular lecture, we are going to finish all the methods that are required for producing data. As I told you, for Fundamentals of Business Stats, this is your first stats class, we are not actually going to produce data. We are going to collect the data that's already available, but you should still be aware of what. So we're going to look at the second half of yesterday's lecture, which is what are the methods by which we collect data. And one of the methods by which we collect data are surveys. And you already have a survey that's going on. So what are the advantages? What are the different types of surveys? What are the different ways we can collect information? Ultimately, the objective is very simple. You're trying to find some information about a population, which is the set of all items that you're interested in. But you don't want to go and take information from the whole population because it can be time-consuming, expensive, inaccurate, so on. So what you do is take a smaller subset of the population and call it a sample. And based on a sample, make inferences about a population. That's really what you're trying to do. So if I want to make inferences about Kent State, I could take a handful of students from this class, and then based on the information given by those students, predict something about something about the university in general. Okay. There are a lot of problems. One of the things we saw last time was bias. That means a way of collecting information that produces a bias and therefore is not accurate in terms of projection. One way the bias comes about is how a person chooses the sample. That's a bias. But the second bias is also when I know what I've chosen. You probably don't, they don't do it anymore. There used to be something called the Pepsi challenge. Anybody remember? Okay. So what was the Pepsi challenge? They basically would say, okay, here are a bunch of glasses filled with cola. Can you tell me which tastes the best? Okay, the person conducting the experiment was from Pepsi. Now, if you look at the soft drinks, cola drinks, which is the sweetest drink in the whole range? Pepsi, right? If you take Pepsi or a classic Coke, you know Pepsi is much sweeter. So, if you like sweet things and you drink Coke, you're going to say, oh, this is not very sweet. But let me tell you this, if you drink Pepsi first and then drink Coke, Coke is going to taste bitter. So a double-blind experiment is an experiment where neither the subject nor the experimenter knows what treatment we are applying. Okay. So if I were to administer a treatment, if I want to figure out what is the best drug, that neither the drug manufacturer nor the subject should know what's happening. That means the subjects are given a pill which looks identical to a placebo, but the person administering that should not be the drug manufacturer, but somebody totally independent of that person. So that is called as a double blind. Why? We are removing the bias that I might have. If I'm the drug manufacturer and I'm administering the pills, guess what I will do if I want to show my pill is effective? Give my drug to people I think are relatively healthy to start off already. Therefore, when they get better, I can say, oh, look, my drug is very effective. Okay, I biased it. So a double blind is where neither the subject nor the experimenter knows what treatment is being administered to which subject. That's a double blind experiment. And most cases, we need to do a double blind experiment to remove bias. The second way we remove bias is through randomization and replication. Randomization basically means I assign the drugs at random. Replication means I assign it to more than one subject. If I can repeat the experiment multiple times, then I get better indication of the validity of the results. Because if I do it to just one person, I don't know, maybe the effectiveness is because of the person or the ineffectiveness is because of the person. But if I do it to 10 people and I get a consistent result, then I can make some conclusions. Okay? So double blind is very important in an experiment, so is replication. Lack of realism, this is very true pretty much in everything we do, and there are just two examples here to indicate lack of realism. Actually, the second example is, I don't think we ever done this, studying the effect of hairspray on rats to determine what will happen to women with big hair. I never had that problem with big hair, but so I'll just leave it with that. So this guy Fisher actually was instrumental in us creating a well-balanced design of experiments. He was really the father of design of experiments. What did he do? He observed that certain fields people were trying to understand whether applying fertilizer, applying moisture, applying sun was effective in producing good crops. But what they were doing is that instead of assigning them at the same time, this is what they were doing. They assigned fertilizer 1 year, and the next year they said no fertilizer. Okay. Think about this. If you assign fertilizer 1 year and no fertilizer in the next year, and you get a different yield in crops, what does that say about the fertilizer? Really nothing much. Why? There are so many things that could have happened 1 year and not the other. We could have got more rain, more sunshine, better conditions, different seeds. So you really can't make any judgment about the fertilizer. Okay. So he looked at the experiments and decided that really there's nothing coming out of this. And what he did is the following. This is what he did. In any particular year, he took a plot of land and randomly assigned parts of the land to fertilizer and other parts to non-fertilizer. Now, the factors that he could not control are going to influence both the fertilizer plots and the non-fertilizer plots equally. That means if I get rain on a fertilizer plot, guess what? The non-fertilizer plot also gets rain. If one part of the plot drains well, the other part is also going to drain well. So what he has done is balance the uncontrollable factors. So now whatever difference you get between the output in the fertilizer plots and the non-fertilizer plots, you can make a better judgment and say that is because or lack of fertilizer. Okay, this is called design of experiments. And now most design of experiments are conducted this way. Okay, so we are really not, again, you'll get this kind of design of experiments when you start taking advanced statistical classes. Okay, but for this particular course, we don't need to worry about it. So we have already seen how to randomize by throwing things into a hat. We can use a mathematical table. In our case, you will actually see that when we do randomization, we will use JUMP. JUMP has a randomization function. In fact, if you go into your JUMP and say choose on tables and choose subset, there is a function there. It says choose 10% of the subset. It will randomly choose 10% of your subset automatically for you. Okay. So we will use actually statistical software to choose randomization. So here is a summary on experimental design. Again, we are not going to do or collect experimental design things, but you should understand the terminology. The first is control. We use a control variable to find out the effect of lurking variables. Okay, so that's really important. So we compare two or more treatments and then we can control for these lurking variables. Randomization, very, very important concept when we're dealing with experimental design. And finally, replication. Replication allows us to get some measure of the validity of the results. Validity is why important because that allows us to experience or estimate the variability that you might experience. Okay, so replication is very important. Finally, this statement in red is going to be used repeatedly. So I want you to, the moment you hear those words, understand. If I say that something is statistically significant, that means the results are different from what you would expect by chance. We will use this a lot when we come to hypothesis testings and confidence intervals. Okay, so here is an example of randomized design. So if I was testing two different diets on, and in this case rats, then we would randomly divide the rats into two groups and apply the treatment to each set of groups. So any difference in treatment would tell you the difference in the diet on the weight gain. Okay, so that's really randomized design. What if I were to separate them out by gender? Okay, and then apply the treatment. That is called as a block design. So this is very similar to the previous design, but notice we now divide the subjects into men and women, and then we assign a random assignment. Now, you might think that this is all so trivial. Let me tell you this. For the large part of our drug testing history, most of the drug effects have been tested only on males. Think about this carefully. That means when people say Advil is effective, when the drug manufacturer actually tested that, it was only tested on males. Do you think there are physiological differences between men and women that the drug may have different effects? So, just because Advil is effective on men does not necessarily imply that Advil would be effective on women. Secondly, if 10 milligrams of Advil is effective on men, does it automatically imply that 10 milligrams of Advil is effective on women? No. Okay. So only recently, maybe in the last 5 to 10 years, is now drug testing done on both men and women. So sometimes you will see the recommended dosage would be different depending upon your gender. By default, for if it's still prevailing viewpoint, by default, the drug testing is done mostly on men. So if you're a woman, you might want to be a little more careful in the recommended dosages. Okay, that's the unfortunate part of it. So. Finally, match pairs. We know that Twinsburg has a twins festival every year. And that's important. Why? Because twins come as close to a match pair. So something you want to decide on a treatment and you want to know, you want to separate out the effects of body constitution, twins are the best matched pair we can get. Okay. So when we pair up subjects, we can do it, that's called a match pair design. Sometimes what we do is we use the same person, but we stagger the treatment over time. The presumption is that the effect of the drug does not stay over time. Okay. And you might be involved if you're especially in the marketing major, they'll sometimes recruit you to be involved in their experiments, where they'll show you different images and ask you which image was more effective to market a product or something like that. That is a match pair design. Okay, because the same person is getting multiple treatments. Okay, and that's also pretty common. So, I don't know. So here is your... The answer is 2. It is an experiment, but not a double-blind experiment. Why is it not double-blind? Because the people searching know what search engine they are using. Okay, if this was to be a double-blind experiment, then the students searching would not know what search engine they are using. Okay, so it is not an observational study because the search engine was assigned. An observational study would indicate that the search engines, the students would automatically use whatever search engine they were using. Okay, their choice. But the search engine was assigned to them, therefore it's an experiment. Okay, so the last part of this chapter, we are going to look at sampling methods. How do we collect data? So we have 4 different sampling methods we are going to look at, starting with simple random samples, stratified, cluster, and systematic. All of them fall under the class of what we call as probability sampling methods. Okay, so we can define the way we collect samples in 2 broad categories. The first one is non-probability samples, and the second one is probability samples. Under non-probability samples, we have convenience sampling and voluntary response, and then we're going to spend a little bit of time on the probability samples. So let's look at the non-probability samples. Voluntary response. Have you volunteered information at any point in terms of somebody asking you things instead of... For example, many times we used to have a lot, thankfully it's slowed down now, a lot of credit card companies setting up all along the plaza, offering free t-shirts, and if you fill out a survey or if you fill out an application or filling out a survey or something like that, right? Whenever they do that, essentially that's either a voluntary sample or in many cases it's a convenience sample depending on how they administer it. Now, are those samples reflective of the population? Do you think the information collected that way will have any problems? How about, I don't know, last time, on TV we used to have those, oh, if you concur with this opinion, dial 1-800 some number. If you do not, then dial another number. Oh, and by the way, we'll charge you 50 cents for dialing and telling us what you think. What kind of sampling is that? That's voluntary, right? Do you, and then they'll give you the results and saying, oh, 75% of the population or the sample said this. Do you see that I could use that information to sort of tell what the citizens are thinking? Is that reflective of, or do you see a problem with collecting samples that way? No problems. Sorry? You basically have a bias, right? I mean, when you do voluntary samples, when do you volunteer? Either you think strongly about it, or you one way or the other, or you're getting something free. Okay, that's the only two times you're going to volunteer. So voluntary samples by definition have bias. Similarly with convenience samples. So what we are going to focus on are probability samples, where the information we gather is more reflective of the population we are trying to study. Okay, so that's where we're going to concentrate on. So, sampling randomly, the first one is called random sampling, but I don't want you to differentiate, I want you to differentiate between random sampling and probability sampling. Probability sampling is the overall class or approach of sampling. Simple random sampling, which we will talk soon, is one type of probability sampling. We are going to study 4 types of probability samples. The first one is going to be called simple random sample. Okay? So let's take a look. So let's take this class. And let's say the class is the population. And I want to take a simple, and let's just for argument's sake, let's say my class population is 100. Okay? Just for argument's sake. So when I write capital N, this is population size. And I want to take a simple random sample of size equal to 10. A simple random sample is taken so that every individual in the population has an equal chance of being selected. So what is the probability that he will be part of my sample based on the characteristics I put down? And I'll do a simple random sample. 1 in 10. Agreed? The probability that any one person is selecting him is 1 in 10. At this point, if I do simple random sampling. Now, of course, I could do sampling with replacement or sampling without replacement. With replacement means what? I take him as my sample, I note down his values, and I put him back into the population. So would you agree for the second sample point, he has the same probability of being chosen as anybody else? If I do simple random sampling? Okay, so think about this. Since simple random sampling, every person has an equal chance of being selected as part of the sample. Okay, that's simple random sampling. Now, let's differentiate that and contrast it to a systematic sample. A systematic sample, sometimes called as a 1 in K, sample, okay, sometimes called as a 1 in K sample, is selected as follows. Systematic has an advantage of being very quick to select. Suppose K is 5 and I want to select 1 in 5. That means out of 5 students I want to select 1 and I want to do it in a systematic fashion. Here is how I would start. I would start with her, and among the first 5 I would randomly select 1. Let's say the second person. Once I select the second person, then I select every 5th person. That's it. So remember this, the first person is randomly selected among the first k. Once you select that person, then I select every kth person. Okay. Now systematic sampling can have a problem. You already figured out, it's very quick. Once I figured out the first person, then I just select every kth. But there is a problem with systematic sampling. Can you think of what? When do you think systematic sampling will run into problem? When was the last time any of you fly? Anybody flew recently? No, nobody flies. What kind of plane did you go in? Okay, how many seats were there in that?
Two on one side and three on the other.
Okay. Okay. And let's say I'm an airline, and I say, oh, look, I'm going to get a sample of my passengers and figure out whether they had a good flight or not, okay? And I'm going to do a 1 in 5 sample. So I say out of the first 5, I'm going to randomly pick one, and I choose, and I get the 4th person. It's 1 in 5, so that means after that, every 5th person. Which are the most comfortable seats in the plane? Not the ones I chose. In fact, that's an oxymoronic because there's no comfortable seats in a plane. Okay. Which are the most uncomfortable seats? That's the middle seat. So when your systematic sample happens to fall into a pattern consistent with your population, we have a problem. Then the results are no longer representative of the overall population characteristic. That is what you have to watch out for in systematic sampling. Other than that, it's a great technique because it's very quick. Okay, so that's the thing that you have to watch out for. Okay, now we're going to get a little more complicated. Stratified sampling. Suppose I wanted to find out how long it takes you to come to school. Okay. How would I do it? If I do simple random sampling, I could just ask at random 10 people and say, oh, based on the time that you have spent, here is the amount of time that the class spends coming to school. Is there a better way of doing it? Can you think of a more efficient way of doing it? Okay, let me ask, anybody volunteer how long it takes for them to come to school?
An hour.
An hour? Where do you stay?
Lake County.
Lake County.
I would have an hour and 40 minutes to school.
You coming in from Canada? Where are you coming in from? Where? Pittsburgh?
No, it's like Medina, Wayne, Ashland County, and
Lorraine. An hour and 45 minutes. Eh? I hope you have about 6 classes today. Okay, that's fine. Get your driving time worth. That's right. Yeah.
Yeah, I was thinking that you would have to do subset categories.
Okay, so what do you want me to break them up into? So you think there are 2 categories of people?
Yeah.
Okay, what are the 2 categories?
One would be walkers and then one would be commuters,
Okay, so the walking category and the commuting category. They look alike, but okay.
You could even do walkers on campus, walkers off.
We could do that. Why don't we just leave it at 2 for the moment? So people who walk to campus and people who commute to campus. Have you thought about renting a plane and landing at Kent State Airport? No. Okay. So would I take the same number? How many people walk to campus? Oh, and that's Probably a little more than 50%, I would say. So would I take the same number of people who live on who walk, and same number of people who drive? Okay, let's try this experiment. People who walk, what is the shortest walk anybody has in that group? Anybody walk in less than 10 seconds? Or no, I'm just picking.
5 minutes.
5 minutes. Where do you stay? 5 minutes is where? Campus center. Campus center. Okay. 5 minutes. Nobody lives in this down the road.
I live across the street.
Oh, so 30 seconds. That depends on traffic.
Yeah, the traffic lights.
Yeah, unless you want to get run down or something like that. Okay, so let's say a minute. What's the longest anybody walks? 15 where? Where? 20 minutes from where? Campus Point. That's on Main Street? Down by Sheets? 20 minutes. Okay. Anybody longer than 20 minutes walk? I'm not talking about taking detours everywhere. I'm just talking coming to class. Okay. Let's talk about people who drive. What's the shortest anybody drives?
3 minutes.
How much?
3 minutes.
3. Where, one parking lot to another one or what?
Main Street.
3 minutes. Yeah, but I'm not asking you how long it's taking you to get parking. 3 minutes. Okay, we already have 1 hour and 45 minutes. So 105. Anybody take longer than 1 hour 45 minutes? Okay. Not yet, that's right. They're not here yet. That's a good point. Okay, look at the two. If I want to get information on the first group and to get information on the second group, would I take the same number of samples? Intuitively, what would you say? No, right? Suppose I tell you can take a total of 10 people. Can you break it up into those two groups? How many will you take from W and how many will you take from C? Did my W sound like W? Or does it sound like a V? Anytime I have to say V, I always say V otka, and that the V comes out correctly. If I say vote, it'll come out as W, right? Yeah. So, first group and second group. If I give you 10 people you can take, that's the amount of money I have. How many will you take from the first group and how many will you take from the second group? 5 and 5. What is your rationale for that? Just seems convenient?
Would it depend on what percentage of the people are in each category?
No, forget that. Let's say we have enough. All I'm trying to do is get an idea about each group. Which one will you have a harder time getting a better idea of? The commuters. Why? What is the underlying thing which is different between those two? Say it again. Variant, that's it. Wouldn't the commuter group have higher variability? Higher variability means larger samples. So to get the same level of confidence in your result, you will have to take a larger number of samples from C than from the first group because the range is smaller. If I could take 3 students from the first one, I'll probably get a decent idea of the average time. But if I take only 3 from the C group, it may all be 3 minutes, 5 minutes, and 6 minutes. And I'm looking at it and I'm saying there's no difference between driving and walking. Okay? So the higher the variability, greater the number of samples. But we have done something here. What have we done? This is called stratification. We have broken up the whole data set into groups where each group is homogeneous. Would you agree that the people in the first group are homogeneous in terms of the travel time in some sense? And similarly in the second group in terms of in commuting time? They're broken up into groups. When we do that, that is called stratification. So a stratified random sample is done as follows. Take the group, break it up into subgroups where each subgroup is homogeneous, take random samples from each subgroup and combine the result to get the overall result. So in this case, I would take, say, 3 from W and 7 from the C group, look at the results, and then make some judgment about the overall population. That is called stratified random sampling. Can you think of another way of breaking this class into groups? Give me an objective and tell me how you could do stratified random sampling in this group. Anyway, it doesn't matter. Class standing, that's right. And the purpose of that would be to, what would you try to get? What kind of information would you want to get? What would be the objective of breaking up the class into class standings? What kind of objective?
What standings, like the average learner, like which majority is in our class, like if we're all sophomores or like freshmen.
Okay, that would be how I break it up. Then I would take random samples, right? But what do you want to study based on class standings? What would that information give you? I mean, do you want to study to see if the GPA is different by standings, or you see what I'm saying? You need an objective, right? So it doesn't matter, but that's a good example, breaking it up by class standings. Okay. So everybody clear on stratified random sampling? Okay, now let me ask you this. If I break up this class into 4 groups, no, 4 groups, 2 groups, okay, which is W and C, and let's say we had 60 people here in our population, I'll call that N1, and N2 here is 40. Oh, are you a commuter or are you walker?
Walker.
You're a walker, okay. What is, and I'm going to select 3 here and 7 here. Remember, when I did simple random sampling, the chance of him being selected was what? 1 in 10. Okay? Can you now tell me what the chance of him being selected is if I do stratified random sampling with that breakdown? There are 60 people in the walking group, 40 people in the commuting group. I want to select a sample of size 3 from the walking group and size 7 from the commuting group. What is the chance that I can select him? One in 20. Very good. Do everybody see this? Do you see the probability has changed of him being part of the sample now? It used to be 1 in 10, now it's 1 in 20. But anybody here, oh, I'll take you. What is the chance she's selected? She's part of the commuting group. What is the chance she's selected now? 7 in 40, right? Her probability has gone up of being selected. So stratified random sampling no longer gives you the same probability. That means every individual no longer has the same probability of being selected. Okay? I'm going to shift gears here a little bit and talk about cluster sampling. Cluster sampling takes a slightly different approach. We still break up the whole population into groups, but with the following differences. Each subgroup looks like the next subgroup. So let me tell you this. We have this class, we have 4 sections. Would you agree that if I take this section, there are people in this section who walk on campus, there are people in this section who commute. Similarly, in this section, there are people who walk, commute. That means if you look at this section, very similar in characteristics to this section, and so on. So instead of selecting or instead of breaking the group, overall group into population into subgroups, where each subgroup is homogeneous, I now break up this population into subgroups where each subgroup looks like a smaller version of the population. There used to be a time when that Austin Powers movie used to be popular, long back. There used to be a character called Me, and there used to be a character called Mini-Me. The subgroups in a cluster sampling are mini-me's. They look exactly like me, but a smaller version of it. Okay? So this is a subgroup which looks exactly like the population but just a smaller version. So in cluster sampling, we do not select individual people. We select the subgroup. We select the whole cluster. So if I were to employ cluster sampling in this class, given we have 4 clusters, 1, 2, 3, 4, and I want to select one subgroup, what is the probability that he is selected as part of my sample? What's the probability? Remember, I am now selecting the whole subgroup. 1 in 4. Because if I randomly select this subgroup, then he is automatically part of my sample. 25%. Do you see? The probability has changed dramatically. So remember this. In cluster sampling, we select the whole group. In stratified sampling, we select individuals from every subgroup. Look at the characteristics of the subgroup now. In cluster sampling, it is heterogeneous within a group, similar across groups. This group looks like this group. In stratified sampling, it is homogeneous within a group, different across groups. Everybody who's commuting in one group, everybody is walking in one group. Homogeneous within a group, different among groups. Do you see that? So, in stratified sampling, the greatest variability is where? Within a group or across groups? In stratified sampling. Within a group or across groups? The variability. Where would you see the greatest variability in stratified sampling? Within a group or across groups? No. Where is it homogeneous in stratified? Aren't each subgroup homogeneous? So the variability, greatest variability is between groups, across. In cluster sampling, the variability is greatest within the group. And each group looks like the other group. Therefore, less variability between groups. That's the cardinal difference between those two. Okay? So, is cluster sample a simple random sample? I might need stronger before I respond to that question. Did you get the same probability for both techniques? Then how can cluster sample be a simple random sample? Answer is no. In simple random sample, the chance of him being selected was 1 in 10. In cluster sampling, it was 1 in 24. 1 in 4, sorry. Not the same thing. Okay. Is cluster sample a stratified random sample? Again, no. In cluster sampling, we select the whole cluster. In stratified, we select samples from every group. Every time the sampling method says, I selected the whole group, cluster sampling. Don't even have to think. Every time it says, I selected samples from each of the groups, stratified sampling. Okay, that's the essential difference between those two. And we already talked about that. Okay, final slide before we get to more clicker points. There are a lot of other issues regardless of the sampling method that we use. The first one is called non-response bias. That means even when you send out a survey, people will not respond. In fact, non-response is a huge problem. Most times when we send out surveys in real life, we are lucky to get a 10% response. That means 90% of the people don't respond. Okay. Probably the only thing which we get a better response is sometimes you have to fill out your student evaluations. Sometimes we'll get a better response than that. But most real life surveys, we never get very good response. So non-response. So just because 90% of the people doesn't respond, doesn't mean that suddenly we can ignore them. We can't, right? What we are trying to get is a feel of what the population is. And here you're saying the 90% don't respond to it. Then how do we make inferences with the 10%? We have to make inferences, but it's tricky. Finally, response bias. So in response bias, we don't necessarily want to respond to what is being asked in a truthful manner, and therefore there is a bias. We might respond either to mess up the survey, or we just feel like being not telling the truth for whatever reason. Doesn't matter. That's a response bias. And the way we word it creates a bias automatically. So, I mean, this is very difficult. The last question is very difficult because most surveys are always worded to expect a certain response. So anytime you're looking at a survey coming from political groups, religious groups, marketing groups, they're always worded in a way to elicit a particular response. And even though you don't realize it, that is creating a bias. Okay? So that is very difficult problem to solve. So, and under coverage, we know with the census. In an under coverage, we already talked about this, and sampling methods actually can get you a better estimate of what the true population looks like. But unfortunately, this is blocked more from a political standpoint rather than from an accuracy standpoint. And the people who tend to object to doing sampling are people who are traditionally rich. Okay, the people who are rich have the access and the means to be counted. The people who don't have the money automatically get left out, and they have the least amount of representation. But from a statistical point, ignoring all the politics, if you really want to get a good idea of the population of the United States, you want to do sampling. Okay, that's the way you want to do. So, and we already talked about the clinical trials. So, we have seen this. So let's talk about some. After this, I'm going to give you some clicker points. Can you tell me what the sample is and the population? What is the population, first of all? Population? Yes? Population. The set of all students at Ohio State, right? That would be the population. And the sample would be the 15 students. What kind of sampling method did they use? Convenience sampling. Very good. This is a approach of convenience sampling. So, a simple random sample of 12,000 adult Americans is selected and asked, in light of the huge national deficit, so on, so on. 39% of those responding answered yes. What can you say about the survey? Did they use a probability sampling method or a non-probability sampling method? What kind of method did they use? Is simple random sample a probability sampling method or a non-probability sampling method? Remember the tree I put up first? What kind of a method is simple random sample? It's a probability sampling method, right? So it's actually a good sampling method. But do you see a problem with the survey at all, if there is any? Yes?
Wording bias.
Wording bias, very good. There is a bias in terms of wording, so. Okay. Okay, let's go. Playing. They selected the whole box. I told you every time they select the whole group, it's cluster sampling. If this had been simple random sample, they would have selected randomly from the 1,000 bottles. Okay? So think carefully on what they selected. That's the key. How can you pick strategy 5?